Good afternoon, everyone, and thank you so much for being here today. I'm here to present my doctoral research, which is structural changes in cellulose pulp under extreme pressure conditions. So let's get started. So I've been living in Sweden for quite a while now, and one thing that Swedish people have a lot of is their love for afternoon fika. No, I'm just kidding. They do have uh, wood, which is in abundance, and most of the land region in Sweden is covered in forests. So there are many economies that are based on forests. And one such industry is refinery, where they take the wood as a raw material and they extract different components of wood, all the way from pulp to nanofibrils and beyond. So one such product is cellulose pulp, bleach pulp, and in its native non-dried format. And this pulp we are going to take as a raw material for our research and expose it to the extreme pressures. Now, what exactly extreme pressure does to the material? We all know the famous example of diamond, when due to the enormous pressure of Earth's crust, the carbon atoms rearrange themselves to form a beautiful diamond. Another research from Harvard University said that if you take liquid hydrogen and if you compress it to roughly 500 gigapascals of pressure, which if you want to put it in perspective, it's blue whale hanging on a grain of sand, that kind of pressure, then you will get a metallic hydrogen, which is a superconductor at room temperature, which is a phenomenal achievement. Another one example from World War II is called picrete. So they tried to take wood, tried to take water, fuse them together, and change the physical condition of water from liquid to ice, and we were getting a durable and hard material. One more example I would like to cite is from Lawrence Livermore National Laboratory, where they tried to take water and compress it with the extreme high pressure shock wave. And that basically said that you can get ice at room temperature in literally nanoseconds. So now the question comes, since we are dealing with wood, does wood experience such kind of pressure in nature? The answer is tricky. Yes, it does, but not in terms of the direct pressure. It experiences it in terms of pressure gradient. So the tree, which is roughly 50, 60 meters tall, they have to transport the water from root all the way up to the tip. And in order to do so, most of the trees evaporate water at the leaves and create a negative pressure gradient. And the water is transported from root to the tip with the xylem tubes, which are located inside the wood. So wood does experience that kind of extreme pressures in the nature. That's where our research comes in, and that's how I would like to define the mind map for my thesis. So we are taking cellulose, we are taking water, and we are exposing it to different kinds of pressure. First one is dynamic pressure using the shock waves, and where the compression and decompression rate both are quite rapid. It's less than 1 seconds. Then the second pressure kind is the static pressure, where we compress the cellulose pulp in uniaxial manner, where the time scales for the pressure application and decompression are more than a minute. And in third approach, we try to combine both of these. So we compress the cellulose in quite slow manner, but then we decompress it quite rapidly to just to see how it affects the cellulose pulp. And this is how I'd like to structure my thesis. So I have a dynamic compression part and I have a static compression part. So in this dynamic compression part, we'll talk about the shock waves and the steam explosion, and the static compression part, we'll talk about in situ and the ex-situ compression of cellulose. So let's start with project one, which is shock wave compression. So if you see the phase diagram of water here, which is a standard phase diagram, water exists in different phases according to the temperature and pressure that it's at. And the way we are looking at the pressure diagram is we want to go from room temperature and atmospheric pressure all the way up to 350 megapascals at room temperature. And the material that we will be using in this experiment was never dried carboxymethylated pulp at degree of substitution 0.1. So it's a low charge pulp and concentration of 5 to 10% depending upon the experiment, nature of the experiment. The philosophy behind the experiment was we will take the fibers, the shock wave is going to treat the fibers, break the fibers, and we will see the effect on the fibers later on. So it was important for us to identify the research gaps, if there were any, and if any kind of research were done in this area. So similar kind of researches were done in this area where they tried to rely mostly on the shear forces. So high pressure homogenization, where they tried to pass the pulp through orifice, and due to the extreme shear forces, you will have a breaking of fiber and you get the nanofibrils. Also, there was one more research which tried to treat the cotton pulp with extreme pressure and temperature conditions, and that basically destroyed the cotton fibers. A few more researchers have highlighted the treating the elastic polymers with the shock waves, and the result was, along with the high compression wave, they also have a shear wave associated with it, which is a very promising thing for us to start with. So to sum it up, we have if we expose the pulp to dynamic pressure, we will have a slightly better accessibility. We will have a surrounding water, which is easy for the pressure transfer as a pressure transfer medium. The current methodologies that are existing, they are a little bit energy demanding, they are time consuming, chemically demanding, and temperature degradation is a major issue in them. That's why identifying all of these research gaps, we wanted to set up our experiment. And the ideology behind this design was very simple. So we have a weight at certain height, which drops on top of an experimental chamber, which is in the form of piston cylinder arrangement. And inside this chamber, you have a cellulose and water mixture. So due to the impact of weight dropping on top of this chamber, we will have a strong shock wave which will be sent inside the experimental chamber. And after many iterations, we were able to achieve this. So in the image A, you can see the experimental chamber, which is roughly 8 centimeter long and 8 millimeters in diameter. And in image C, you can see there is an electromagnet on the top, which holds the weight at certain height, desired height. And upon electronically triggering the signal from computer, we can drop it on top of experimental chamber, which will be kept here. Now there is also a laser pointer system, which is monitoring the motion of the drop weight at every time step. And also there is a load cell at the bottom, which is recording the pressure versus time data at every step of the way. So as a researcher, as an engineer, I was satisfied, but as a scientist, it was curiosity that for me, whether it actually works. And to our fortune, it actually worked. And you can see in the image A, you have fibers before the treatment. And from the image B to D, you have fibers that is going from low level of shockwave treatment to extreme high level of shockwave treatment. D being the shockwave produced from 1,500 millimeter drop of the weight. So now we know that it has a definite effect, but we wanted to quantify that effect in terms of what exactly is happening inside and how exactly shockwaves are able to disrupt the structure. So we tried to estimate the pressure. So as I said before, there was a load cell at the bottom, which was recording pressure versus time data. And this is the data that I've plotted here. And if you notice, as you increase the drop height of the weight, then the wave is getting sharper and sharper, which is very intuitive. Then, according to the maximum pressure and the drop height, we are plotting this calibration curve that will give us the correlation between the drop height and the maximum pressure that is achieved inside a chamber. Now, we wanted to see how the shock waves are interacting with the material inside. So we wanted to go a little bit on the computational approach. So we employed simple Euler's equations in a conservative form. We have different variables to be conserved, and that's namely the density, X momentum equation, R momentum equation. X and R are the directions that I have shown here in the experimental chamber, and energy density. Also, F and G are the fluxes in R and in X and R direction respectively. Now we know how the properties are moving inside the fluid, but we wanted to relate the pressure and density. And for that, we are using the Tate equation of state, where pressure is related to density in linear as well as non-linear manner, because the density is going to be variable when we are talking about the shock waves. So with all of that in mind, when we tried to plot the shock wave graphs, then we understood that the shock wave we are getting is traveling inside a pressure chamber in very small amount of time. So if you look at the time steps that are mentioned on the top, that's time step is roughly about 0.05 milliseconds. So if you think about this as a shock wave of, let's say, 1 Mach number, that roughly translates to 1,500 meters per second inside water. To cover the 8 centimeter distance of the experimental chamber, it takes roughly about that time, 0.05 seconds. But if you look at the previous, if you recall the previous graph, the force versus time graph, then the actual impact time is roughly about 10 milliseconds. So what exactly was happening during that 10 milliseconds? The shock will be passed. The shock will be covering the 8 centimeter distance. It will hit the bottom. Since it's hitting the denser medium, it will reflect back. And while the contact between the impactor and the piston is established, that will send in another shock wave, and that will interact with the reflected shock wave. And this phenomena will occur multiple times as long as the contact between the impactor and the piston is established. So if we want to see it in a bigger perspective, so here you can see that after a few waves have been passed, the shock wave no longer looks like a sharp vertical wave. It more or less translates as a horizontal component. And if you look at the yellow wave, which is a little bit later in the time step, then it's actually going up at the bottom. So that means it has already started to reflect back. And if you imagine a cellulose particle in here, then due to the shock wave, it will experience enormous compression forces. And this is the incidence where we have isolated the reflected waves. And if you imagine the same particle here, then after it has been passed through the shock wave, it is under the compression forces. And when you treat it with the reflection wave, then it will experience a little bit of relaxation. Now, as this phenomena occurs hundreds of times, if you zoom it here, you can see that the stepwise function, we are getting sort of like a stepwise function, and the increment in this step depends upon how the incoming and the reflection waves are interacting with each other. So any particle which is in this fluid regime will experience compression, tension all together every step of the way, as long as the contact between impactor and the experimental chamber is established. And also from the literature, we know that every shock wave is having a shear wave associated with it. So the particle goes through compression, relaxation, compression, and shear forces all the way along the line. And that's exactly causing the fiber breakage. That's the bottom line for this. In order to see how the material is changing, we try to do the X-ray diffraction and the wax measurement. So basically, we have a material which we bombard with X-rays, and the diffracted beam is collected at the detector, and after post-processing, we deconvolute different peaks. It's a very standard procedure, and we use some standardized equations to calculate crystallinity as well as the crystallite size for 200, which is a major crystalline peak in cellulose. So just off the top, just from the observation point of view, you can see that the crystallinity index was showing a decreasing trend. So as we are increasing the intensity of shock wave, the crystallinity of cellulose was going down. Also, the crystallite size for 200 peak, which is here, the major crystalline peak of cellulose, that was going down, which is very intuitive considering the crystallinity is going down as well. And the same phenomena was also repeated in the wax measurement, which was done on the wet samples. So we have a decreasing trend in the crystallinity as well as the crystallite size. Now, if this were true, then we will also have a little bit of surface fibrillation as well as the nanopores, which will be opening up. For that, we did some Sachs measurement. And after this is what a typical Sachs profile looks like. And after all the post-processing data, what we ended up with is a Sachs curve where we tried to fit the autocorrelation functions and SCF so that we can get the actual computational fit for the Sachs data. And with that, we have several components that we have established. So I1, I2, and I3 are the abundance of the particles that we will be dealing with, and average apparent particle size and average apparent cavity size are the two parameters that we have introduced. Particle size being the size of the particle inside the system, and cavity size belongs to either the pores in the system or the distance between two particles. So if you look at the particle size distribution for I1 and I2, which belongs to particle size of roughly 5 nanometers to 15 nanometers, you will have increased abundance. And it's not coming from anywhere else. It's just breaking down of the bigger, higher order particles to these particles. And also, if you look at the AACS, average apparent cavity size, then you can see increment in the cavity size of roughly 40 nanometer cavities. So if we want to establish this as a process, then we wanted to see how are the losses looking like in our system. And you can see the energy provided to the system and energy which is going towards the actual production of shock wave. There's a lot of difference. And major difference is coming from the frictional losses that the weight is carrying while dropping on top of a chamber. And also some of the instrumentation that we have used, it's not really relevant to the shockwave production, but we need it for the characterization of shockwaves. Also, if you look at the energy required to treat 1 kilogram of sample, even for the highest level of treatment, which is 1500 millimeter of drop, it's about 600 kilojoule, which is quite comparable to single pass homogenizer, even less than that. This setup was referred to as SSR by Daniel and Thomas in one of the meeting that we had. And one time we were discussing about this project, and I happened to go out of the room for 5 minutes. And when I came back, Thomas and Daniel, they were referring to it as SSR. And as a PhD student, I didn't want to sound stupid. I thought it's a very established something from the industry that I don't know about. And after 1 hour, the discussion went on, and they keep mentioning SSR, and the curiosity got the best of me. And I ended up asking them, like, what exactly is SSR? So Daniel mentioned we have renamed your setup now, and it's called Stupidly Simple Refinery. That's exactly what it's doing. Moving on. So we will talk a little bit about static compression experiments, where we wanted to establish a little bit of literature review, and here we were a little lucky because there was some research done in this area. So one research from Portugal, they compressed the cellulose pulp at roughly 400 megapascals of pressure, and they reported a little bit higher crystallinity. Also, there was one research that did the bulk compression of cellulose, and they established a relationship between cellulose volume versus temperature and pressure, and it was a non-linear relationship. Also, another research suggested that as long as you have a pressure transfer media in the liquid form, it will have a certain trend in the volume, lattice volume contraction. And when it changes to the solid due to the extreme pressure values, the trend in the lattice volume contraction will change. Also, there was some research done on the cellulose, compressing cellulose at extreme pressure. Most of them were done on the dried cellulose samples. This is not something we were looking for. We were looking to compress the cellulose in its native non-dried format. But still, this provided a solid methodology for us to base our work on. Also, there was a foundational research from Nishiyama, which helped us in calculating the cell lattice parameters for cellulose. So let's start with part 1, which is the in-situ dynamic compression. So in the water phase diagram, where we wanted to be is we started with the room temperature again, and we wanted to go all the way into the crystalline ice form. So if you start compressing the water at roughly 1 gigapascals of pressure at room temperature, you will hit the ice 6 region. So the water will rearrange itself in compressed ice form. And if you keep on compressing at roughly about 2 gigapascals of pressure on 1 gigapascal of pressure, you will hit the ice 7. And at 1.8, 1.81 gigapascals of pressure, ice 7 crystals will start to appear in a metastable form. So they will not be a stable crystals, of course, but they will get stable at roughly 2 gigapascal pressure. The material that we will be using is the same material as before, so never dried carboxymethylated pulp. Also, we have added the never dried craft pulp in this setup. And experimental philosophy was we take tiny amount of sample, we compress it between two diamonds, we shine the X-rays through them, and we see how the material is changing its structure while it's doing so. So this was the experimental setup where you can see the tiny amount of sample is compressed between two diamonds. There's a ruby crystal which is helping us to find out the actual pressure during the experiments. The X-rays are coming in, they are detected at the detector, and we found the diffraction pattern of the cellulose through this. In image B, you can see there is a measurement grid, which basically means we have measured the cellulose sample in different areas. And also this was to prevent any of the radiation damage that we may get during the synchrotron experiments. This experiment was conducted at extreme conditions beamline at Desi, Germany. And after post-processing the data, we came up with the XRD patterns for both never-dried craft pulp and never-dried carboxymethylated pulp. In case of carboxymethylated pulp, we were able to recover a decompression signal. So once we were done with the experiment, we recovered the cell and we waited long enough to get the decompression signal. That was basically the signal that we could record. And just from observation, you can see the peaks are having a rightward shift. The 200 peak is having a rightward shift. Rest of the peaks are not quite clear here visibly, but one peak that you can see quite clear is this one. And we wanted to quantify all of that. So we wanted to see how the crystallinity is changing, since in the literature we have seen changes in the crystallinity. So for never-dried craft pulp, we saw there was a gradual increase in the crystallinity with the incremental application of pressure. Also, the crystallite size was getting bigger. That could relate to co-crystallization. Also, when you have a little bit ordered structure, the lattice microstrain should go down, which when we calculated, it was correlating and it was going down. The similar kind of results were also seen in the never-dried carboxymethylated pulp, where we were seeing the steady increment in the crystallinity of the sample, and for the decompression signal, we could see that the crystallinity was going down, but it did not go all the way down to its original value. It had some permanent deformations. Also, the crystallite size was getting bigger in size. Again, could be relating to the co-crystallization, and the microstrain was going down, which is an indication of more ordered structure. Now we wanted to see how the lattice is getting distorted, so we calculated the p-value, the lattice spacing between for different crystalline peaks, and we could see that all of the crystalline peaks, the three that we could recover, 1, -10, 110, and 200 peak, all of these three peaks showed a decreasing trend. That basically means we are pushing the lattice planes together, as it's demonstrated here. And this was also seen in the dried cellulose case in the literature that we have seen. So we were working our methodology off of that. So we calculated the cell parameters for volume contraction, possible volume contraction that we could have. And after some geometrical rearrangement, we could find out that we could actually plot the volume data for cellulose cell and in both craft pulp as well as carboxymethylated pulp. And we tried to fit a mathematical curve through it, which turned out to be Birch-Mungan equation of state. And we tried to do that just to have a mathematical edge on this project. Also, the gamma angle, as you can see from the cell volume, is seemed to be increasing in the beginning, and then it was asymptotic. When it's increasing, that means the majority of forces acting on the lattice plane are shear forces, and later on, at more than 1 gigapascals of pressure, it was more asymptotic, which means that the only force that was acting on the lattice was compression force. So moving on to part 2, so where we did the ex-situ uniaxial compression of the samples. So where we wanted to be in the water phase diagram was exactly in the similar regime as that we did in the in-situ experiment, except we also wanted to explain the high temperature regime in the same pressure area. The material that we use is very similar to that of the first experiment. So it was the never-dried craft pulp and never-dried carboxymethylated pulp at roughly 10% concentration. And the experimental philosophy was we take the bulk amount of sample, we compress it in a uniaxial press, And after the compression, we take the sample out and do some measurements, average measurements, so that we can have a better idea of how the material is changing over time. This was the experimental setup that we developed at KTH, and we have a hardened piston at the top, which is pushing the sample inside this experimental jacket. And the sample itself was contained inside an aluminium capsule, which is spot welded to avoid any leakage. On top of that, we had a UV cured glue, and on top of that, we had a PDMS coating, and all of that to ensure a smooth pressure transfer between the system. So if you have a hard metal to hard metal contact, there might be a chance that you might break the system and you might break the capsule. And this was just to ensure the uniform and smooth pressure transitions. Now, this was the sample before the compression. So A and B are the Kraft pulp, quite focused image of the Kraft pulp, and C and D are the focused images of carboxymethylated pulp. And we wanted to see how it's changing with the pressure application. So at 1500 megapascals of pressure, we could see most of the pores that were closed down, and the system looked completely different. So now we wanted to see the bulk measurement. As I said before, we did some wax measurement at room temperature as well as at elevated temperature. So for Kraft pulp at room temperature as well as elevated temperature, we saw there was a little bit increment in the intensity. Just from the visual perspective, there was a little bit more intensity of 200 peak. That was again indicating towards the higher crystallinity of the sample. But in the carboxymethylated pulp, however, the system was a little bit messy, which we wanted to explore further in the computational manner. So the reason behind this could be that when you have an inaccessible water, when you have a slightly accessible water in the system, and when you have a free water in the system, and when you're trying to compress this system, except the very inaccessible water, most of the water is squeezed out, and you have a fibril bundle, which is a compact structure, and that fibril to fibril interaction and the signals that are producing due to the interfaces, that is contributing towards the higher crystallinity of the sample. So we wanted to see how the crystallinity and crystal structure looks like. So we did the crystallinity analysis, and as expected, Kraft pulp was showing higher crystallinity as we increase the applied pressure. So from 0 to 1500 megapascals of pressure, it was showing a continuous increment, as well as the crystallite size was getting higher. And in case of carboxymethylated pulp, as we have seen, in case of the room temperature, we hardly saw any increment in the crystallinity at 500 megapascals, but at 1500 megapascals, we saw again a little bit increment. And in case of elevated temperature, the carboxymethylated pulp was showing actually a little bit less crystallinity at 500 megapascals, and again it was going a little higher at 1500 megapascals. So this could be because one speculation that I came up with was because of when you have a charged system, when you have fibrils which are negatively charged, and when you're trying to push them together, the repulsion forces between them is at 500 megapascal. It's not able to overcome the repulsion forces, and at 1500 megapascals, you have overcome the repulsion forces and you have brought the fibrils together. That's why we are having higher crystallinity. To support this data, we also did the solid state NMR, which was done with rice. And in solid state NMR, we pretty much saw the similar results. So for Kraft pulp at room temperature as well as elevated temperature, we saw an increase in the crystallinity. And in carboxymethylated pulp, we saw a little bit decrease in the crystallinity at 500 megapascal, but then it was again going up at 1500 megapascals. So we also did the SAX analysis similar to project 1 in this case, and we could see that at room temperature as well as the high temperature, the particle size for Kraft pulp and carboxymethylated pulp, which was going higher, it's roughly of the order of magnitude 4 to 15 nanometers. That was getting lower in number, lower in abundance. And also the cavity size, as we have seen in the SEM images. So the cavity size was getting shrunk. So we have also seen that trend here. So the cavity size was getting smaller in size. So moving on to the final, we want to lightly touch the steam compression project, where we have a lot of literature, and almost all of the literatures found fair success in now producing the nanofibrils. But the major problem with these setups is these are extremely energy intensive setups. Also, they require a lot of chemicals to work. And there is an issue of temperature degradation. We tried to tackle at least one of those issues. So we tried to avoid the use of chemicals at all. And in the water phase diagram, we could not go much higher in the pressure, of course, because it's a saturated steam. And at 210 degrees of temperature, we have roughly about 2 megapascals of pressure. And the samples that we have used is never dried softwood dissolving pulp and the dried softwood dissolving pulp. And both of them have most of the hemicellulose and lignin removed. And because of that, it's quite inaccessible structure, and we wanted to see if steam is able to penetrate any of them. There's also a sample which is called circulose, which is a recycled fibers from the fabric. And there is also a lignocellulose sample, which has roughly about 17% lignin. And this is an experimental setup where we try to treat the sample in this regime, in this experimental reactor, where we load the sample from top, it treats it with the steam at certain time span, whatever we have decided on. And after the experiment, we open a small opening here. And with that valve, we are quickly and rapidly rushing out the sample through a small orifice. So all of that is creating the steam pretreatment on the cellulose fibers. So just from a visual perspective, the softwood dissolving pulp, which was dried and re-wetted. So when we treated it with steam, it was almost unchanged, and this was expected since we are drying the softwood dissolving pulp. We have pretty much closed all the pores, and the structure is very inaccessible for steam to make any differences. For the softwood dissolving pulp, which was never dried, it had a little bit less honification altogether, and steam had a little bit more area to access. And in that case, we saw a little bit surface fibrillation compared to the dried cellulose. In case of circulose pulp, we have seen a little bit surface fibrillation as exactly similar to what we saw in the never dried dissolving pulp. And in case of the unbleached lignocellulose fibers, we saw most surface fibrillation. Again, this is very intuitive since you have a fiber which has lignin, which is readily removable at higher temperatures. Also, when you remove the lignin and when you remove the hemicellulose, you have a lot more accessible surface area of the fiber for steam to do the pretreatment and break down the fiber. So this sums up my entire thesis mind map. And to conclude the entire argument, we have established how we can treat the cellulose in 3 different ways: with the shock waves, with the static compression, and with the steam explosion. And each method provides their individual perspective on how cellulose structure can be changed. Particularly from shockwave treatment, we have increased accessibility to the surface area. After the shockwave treatment, we have shockwaves which are disrupting the fiber structure completely. And this could be a process that is a chemical free, and it can be converted into an industrially scalable process. Second project, which was more of an exploratory project, where we tried to establish higher crystallinity after application of gigapascal levels of pressure. Also, we could see how the lattice is getting deformed, and we could mathematically fit a curve through it to understand it for the high pressure processing in the future. Also, there was a steam explosion project, although it's a very harsh treatment in terms of temperature, but it was still good treatment in general to form nanofibrils at lower quality. And it's already an industrially scalable process, so it's one of the good processes to work with. So to conclude the argument, I would like to say that the extreme pressures can either make the fibers or break the fibers depending upon how it's applied. So in terms of future work and limitations, we have a scalability of experiment in the shock tube experiment that we have done. And this has already been worked on at the fluid physics lab. And Professor Michael Liverts is working on this one. So we have a cellulose sample at the center of this tube, and upon exploding the high current wires, we will send in the circular shock waves inside the sample chamber, and it will treat the cellulose pulp at roughly 10 gigapascals of pressure and 1000 degrees Celsius. And this entire phenomena happens in literally nanoseconds, so we could get a fibrillate cellulose in nanoseconds. And the in-situ study, there were a lot of limitations in the in-situ study this time, and this could definitely be worked on. We could not recover the 004 peak, which is essential for the lattice volume C parameter, which we could not recover this time. So that would be a really nice addition to the in-situ study. And the steam explosion project can definitely be optimized on, since it's already an industrially scaled project. At the end, I would like to thank Voluntary Wood Science Center for funding my research throughout the years, and Research, Daisy, and Rice for providing the support in the experiments. Also, Professor Daniel Söderberg and Professor Fredrik Lundell for supporting me in my academic journey, technical and otherwise. Also, Professor Thomas Larsen and Professor Nicholas Apazidis for providing innumerous hours of technical support, and whenever I was asking for it. And thank you so much, everyone, for listening. And yeah, thank you.